Alright, so today we'll be taking a look at a problem that came from the second quiz of the 2018 fall semester regarding property tables. Basically, we just have to fill in the blanks based on the information they already give us. It's pretty straightforward, honestly, but before we start doing the problem itself, I'd just like to go through some basic concepts that we need to understand beforehand. Before going any further in the video, I'd just like to say that if you guys have never seen this graph before, you don't really know what it represents, please just get accustomed to it beforehand because some of my explanations will be based on the fact that you guys should know this and there's no point going through an explanation that you won't understand. Now, with that being said, this is in fact a temperature to specific volume graph, and the point of me showing you the graph isn't to really explain the intricate details of the graph itself, but it's to simply state that the overall behavior of the graph is also true for a TU graph, so temperature to internal energy, and a TH graph, temperature to enthalpy. Now, what I mean by overall behavior, I mean that there will be a compressed liquid region, a saturated liquid to vapor region, or a saturated mixture region, and a superheated vapor region. For the same TV graph, I highlighted for two separate pressures, the saturated liquid points and the saturated vapor points. Anything between those 2 points for the given pressures belongs to the saturated mixture region and has what we call equality. Now, anything outside of the saturated mixture region, whether it be the compressed liquid region or the superheated vapor region, has no quality. What I mean by no quality isn't that quality equals zero. I mean that quality is irrelevant to those specific phases. Now, I'll be more specific as to what exactly quality is mathematically in the next few moments, but for now, just keep in mind that if we give you quality in a property table, that means that the phase in question has to be a saturated mixture phase. Keep in mind that everything that I've said so far about TV diagrams is also true for PV diagrams. Alright, now let's talk about quality. So the reason I said that the TV diagram also acts like a TU or a TH diagram, it wasn't to simply add more information than necessary to the video, it was to explain these following formulas. So since they act the same way, all of those graphs have a saturated mixture area, meaning that they all have an area where quality can be observed. And given that they behave the same way, the formula describing quality for each of those variables is also the same. So the variable y is basically a substitute for v, u, and h. Now the subindex f represents the variable observed at the saturated liquid point, and the sub fg refers to the difference between the variable at the saturated vapor point minus the saturated liquid point. And the y with no subindex refers to the variable observed at the current phase. Now, quality is also specifically defined as the ratio of the saturated vapor mass to the total mass of the system, which means that quality will be equal to 1 at the saturated vapor point and 0 at the saturated liquid point. So this is an example of a saturated property table of water based on temperature, which I think we should be using in the example presented at the start. Alright, so back to our problem. So let's start with the first line where we are given a temperature and a internal energy. The first thing we want to figure out is whether or not this is within the saturated mixture region. And to do that, we'll see if the internal energy falls between the internal energy of the saturated vapor point and the saturated mixture point at the given temperature, which is 150 degrees Celsius. So we open up the saturated water property table and we go directly down to the 150 degree Celsius line. And then we start looking at the internal energy at the saturated vapor point and the internal energy at the saturated liquid point. And we notice that the internal energy that is given to us in the table falls between both values. Now that means that we are indeed in a saturated mixture phase. So given that, we already know the phase, and we can determine the pressure given that it's the saturation pressure, which is on the same line, 475 kilopascals. Alright, so the only thing that is left unsolved for is quality, and given that we are indeed in a saturated mixture phase, that means that quality does have a value. Now we do know that the internal energy isn't equal to either the internal energy of a saturated vapor or the internal energy of a saturated liquid, which means that X, or quality, is not equal to 0 nor 1. So we have to go back to the table, find the value of U of F and U of Fg to plug them adequately into the equation of quality, which, yes, you do have to remember for the exams. But it's pretty simple. And the value of Y, or U, is given from the table, which is 1,595. Now, once you do the ratio of the difference over U of Fg, you end up with a quality of 0.5. Alright, so now we'll solve the last line of the table. We are given a pressure of 600 kilopascals and a internal energy of 3,477. So now again, as was the case with the previous line, we'll simply go check in the saturated water property table to see whether or not we are indeed in the saturated mixture range. So we open up the saturated water property table, which this time is organized in terms of pressure, and we go down to the 600 kilopascal line. Now we check again if our internal energy falls between the internal energy of the saturated liquid point and the saturated vapor point. And we realize that actually our internal energy is greater than that of the saturated vapor point. So if you remember the PV diagram, which again acts the same way as a PU diagram, we can notice that if you fall on the right hand side of the saturated vapor line, you are actually in the superheated vapor region. So that means in our case, we are actually in a superheated vapor region. That means that our quality is irrelevant and does not apply to that specific phase, and that we are actually in the wrong property table and we have to go to the superheated vapor property table. So now we open up the superheated water property table and we go to the 600 kilopascal subtable, and then we try to find which of these points do we have an internal energy of 3,477. And we end up having that specific internal energy at a temperature of 700 degrees Celsius. Now, if our internal energy were to fall between two values, that would mean that we would have to do a linear interpolation to find out which exact temperature our phase is at. Now, in our specific case, we did have to deal with a superheated water, but if our internal energy was actually less than that of the saturated liquid, then instead of going to the superheated water property table, we would be going to the compressed liquid water property table and doing more or less the same exact process. So the only thing that's left to do is to plug in our final answers for the last line. We did find a temperature of 700 degrees Celsius, a quality that was irrelevant to the state that was observed, and the state in question was a superheated vapor. Now it's important to note that these types of questions should, especially just 2 lines, should take you 3 to 5 minutes, no more. I did take a lot of time to explain the theory behind it and whatever, but when you're doing these numbers yourselves, you don't need to explain to yourself the theory. So once you understand how to go through and parse through the property tables, which honestly, I did explain it, but you need to do it yourself to really get a grasp on it. Once that's dialed down, these numbers can actually allow you to save up some time during exams and maybe review other numbers you aren't too sure on. So thank you very much and have a nice day.